move to the next presentation, which is a recommender system for heterogeneous and time-sensitive environment, presented by Meng. Thank you.
Morning, my name is Wu. I'm a data scientist from EA. Today I got to tell you something about our recommender system. EA is one of the largest game company in the world. We are interacting with over 100 million players by producing some of the most famous sport franchise like FIFA, NBA Live, Madden in American football, NHL. We also have quite a lot of multiplayer shooting like Battlefield, Star Wars Battlefront. Also has some very different genre like Plant vs. Zombie, Need for Speed, and car racing. Traditionally, game companies are not a big player in the recommender system, but as our game becoming more data-driven and a live service, we found out there are a lot of opportunities for a recommender system to help to improve player experience. So we had some brainstorm, and we found out recommendation can be everywhere in the game. It can recommend what to play, like the new game, a seasonal event. It can also impact how players play our game by suggesting what map they should play, what weapon they should use, milestone, mission to complete, skill to practice on. Last but not least, it can recommend a teammates for you or a client to join or AI agent to assist you in the next battle. We were very excited about launching recommender system in our game. So we were discussing with the game team. They have a game 6 months to release. So we start asking, can we have some training data to play with? The answer is no, because no one has played the game yet. Makes sense. And then can we know some content and metadata about this game? And they said no again, because they are still developing the game. They won't sure until the game release. Okay, then we ask, how about we wait for a month after the game release, collect a month of the data, then go from there. And they still say no, because month is too late for us. Because players jump into our game on the very first day. Waiting for a month means we are probably going to miss half of the players. So you can imagine building a recommender system that has no data, no knowledge about the content, and it has to work on the very first day. It's a very challenging problem to us. So we quickly realized the challenge comes from 2 parts. The first part is heterogeneous, because every game tends to be creative and it has to be unique to succeed. Another part is very time sensitive. At EA, we release almost 10 new games every year. It means we are facing this cold start problem almost every month. And not to mention, players are progressing the game. So today they are level 0, tomorrow they are level 10. Their game experience are completely different in our game. To make the recommendation work, we take a step back to rethink almost everything, how we build this recommender system, including system architecture, data pipeline, and algorithm. For the time limit, I will focus on the algorithm part of the recommender system. Let's start with the wide and deep model. It's pretty straightforward. You have wide and deep feature and combined together for the output layer using a sigmoid or softmax to do some prediction. It's pretty straightforward end-to-end model and works very well. But we're thinking training an end-to-end model every time can be a lot of work. So can we have some part of it shareable? So we decided to split it into 2 parts. At the very final layer, we decided to train it to adapt to each application. And before that, at the bottom, we're trying to create a unified feature pool where we can, using a lot of methods to generate a feature. Those features can be application agnostic, and such as standard aggregation, latent factor, also deep embedded feature. Sometimes we also find segmentation is a very useful feature for powering the recommendation system. With that, we still have to train the final layer very frequently. We think it's still some hassle So we decided to go with reinforcement learning by using a contextual multi-app bandit system with a final layer. With multi-app bandit system, you have a good exploration and exploitation, and it's doing a prediction of expectation and the confidence at the same time. Because of that, there's some limitation that you cannot go to a very complicated model. A lot of times people use linear and Gaussian assumption for the contextual multi-app bandit. You could easily have a typical problem like a feature correlation and missing value. In addition, contextual multi-app bandit is an online learning model. If you want to tweak something, it's highly likely to add some interruptions, setting you to ground zero. You have to retrain the model in the online learning stage. To solve those practice problems, we further adding a naive assumption. This is very similar to the naive base that you learn in any machine learning class. With naive assumption, you assume every single feature in our feature pool can make independent prediction. Then we combine this prediction with some ensemble by doing moment matching to get a final prediction. So you can see we have two layers of small arms, and they are rolled up to the final for multi-app bandit to make decision. With the naive assumption, you don't really care about how many features you have at every time. Therefore, you can do more automated feature selection based on the availability, based on the predictive power, and the people who operate this recommender system, you can always do a hard plug in and plug out of the feature without any interruption. You may have some concern about naive assumption. The answer is not that bad. So we did some generic simulation with 10 arm and 50 feature with some correlation. We see the naive linear outperform some traditional linear multi-app bandit algorithm. The reason is very simple, because with linear UCB, you have to have a good estimate of the covariance matrix, which is n squared, n is the number of the feature. But with a naive linear, you only need to worry about the n number of variants. You just need to get those small number of variants correct. So with a system like this, we have a very small team operate the recommender system. We get it to work in more than 10 games and 40 different applications in those games. And we have conduct over 100 experiments. We try to automate everything as much as possible. And in a lot of time, we can go from 0 to 1 just in 1 week. That's including integration, setting up model, doing experiment, and all the end-to-end tests, trying to make everyone's life easier. Some example, like we have subscription service that player can free to download and play any game. So we try to have recommender system to suggest a game they might also like. We compare the MAB versus collaborative filtering. We see the trending and seasonality play a big role, and this helps multi-app bandit to perform well. But you can still add to the collaborative filtering, but it takes some additional work to do it. In another use cases, we are doing map and game mode recommendation. For a game, have a huge number of combination between map and game mode. They require different strategy, different skill, and cooperation. So we are thinking, can recommend our system to help us to suggest the most suitable map and game mode combination. And here we are also interested in different metrics to optimize on. So we select click-through rate versus player retention. As you can see, the orange line, which is the multi-app bandit model, using retention of the feedback. It does not have the fast click-through rate, but the daily active user have been increased most by setting up different feedback. And all those change is just a single line of the configuration in our system. I want to conclude my talk with 3 simple words: power made easy. Lots of time when we're building our recommender system, we're always thinking about power. How can I get the most accuracy? But I want to encourage you to think about how you can make your system easy. Easy means for means it's easy for you to operate, to maintain, to update, and also easy for your product engineer team to integrate it, and for your marketing team to easily to use it. With a powerful recommender system made easy, it's a win-win situation for all of us. And that's all, and thank you for your time.
Okay, we have time for questions. Any question? Okay, I have a very quick question for you. So you tried all this neural stuff, okay? But did you also check other possible approaches before adopting this algorithms?
Yes, we are using a neural network as only a way of producing some embedded feature. We also have library filtering and also like association rule working under the same system.
Yeah, and I have another very quick question about this associations rule. So it's not clear to me if they are manually maintained or they are automatically maintained. And in case, could you tell us about the effort in maintaining this rule, because this is always a problem in this kind of system.
Yes. For maintain, we have to set up some training pipeline and have some strategy at some frequency to update those things. So they require quite a lot of work to set up the scheduler, set up the job, and monitor. So that's also true for any other part of the system. Like even bandit, we always run through some monitoring, some always online testing of it.
Okay, thank you. Oh.
Yeah, thank you for your talk. Question is about, weren't there any rules about game promotions and or business, sponsored things that you had to incorporate within the recommender system?
Yes, there are a lot of rules, especially in a game company, you want to really protect the teenager from really get addicted to the game. In part of our recommender system, we have to be setting a lot of business rules in certain content, and also have to follow all the regulations in different countries, including GDPR.
Okay, other questions? Okay, so let me personally thank you guys for Star Wars Battlefront and all the time that I spent with that video game. And let's thank the speaker again.